Hello everyone, and thank you for attending today's webinar. My name is Jeff Kenvin, and I am the Technical Director at Micromeritics Instrument Corporation. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you can use. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We will try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's webcast and will be emailed to you once the session has concluded. I'm pleased to introduce today's speaker, Hong Nguyen. Hong joined Micromeritics in 2019 and was promoted to his current role as an application scientist in 2020. Hong's expertise are in the areas of surface area, porosity, chemisorption, and temperature program methods. Hong, it is an honor for me to introduce you today. We are so glad you could be here to share your insights on temperature program reduction of copper oxide nanoparticles on alumina, understanding the effects of particle size and surface chemistry.
Jeff, thank you for the wonderful introduction. Good morning and good afternoon, everyone. Thank you all for participating in today's webinar on the temperature program reduction of copper oxide nanoparticles on alumina support. Today we will take a close look at the temperature program reduction method, a brief introduction on the instrument, highlighting key features that was advantageous for this TPR study. We will examine experimental conditions with a discussion regarding Monti and Baiker as a model to determine the best operating conditions when performing TPR. The sample under study is a commercial copper oxide nanoparticle supported on alumina. Some additional characterization was done alongside the TPR. The sample is used to demonstrate how the analysis conditions, such as the active gas flow rate, concentration of gas, the temperature ramp rates, and the amount of reducible species has an effect on temperature program reductions. Lastly, we will end with a case study comparing the temperature reduction of the alumina-supported copper oxide nanoparticles to a pure copper oxide metal powder to juxtapose the effects of the support material and the particle size in TPR. Temperature program reduction evaluates and determines the number of reducible species and the temperature at which the reduction occurs. It is typically used for the characterization of reducible metal oxides and a useful guide for determining catalyst activation or regeneration. It also gives information regarding the reduction mechanism, oxides present, or the interactions between the oxides and the support. Hydrogen is the most commonly used reducing gas. This probe is able to diffuse to small pores and the bulk of the sample, allowing reduction of reducible oxides in the bulk support as well. A simplified equation is shown below. A metal oxide reacts with hydrogen to form pure metal or other transitional oxidation states and water vapor. The feasibility of the reaction is related to the changes in free energy in the system. With a negative change in free energy, the reduction would be favored. At high enough temperatures, positive standard free energy change can be negated by the second term, or the gas constant times the temperature times the natural log of the partial pressures of water to hydrogen. The figure on the right has the standard state free energy of metal oxides. The ones in green are metal oxides that are reducible, and even with a positive standard free energy change, such as chromia and zinc oxide. There are two models for the reduction mechanism of a spherical bulk oxide. The first is a nucleation model. A slow formation of nuclei forms at the start of the reduction. Then, as the nuclei grow and new ones appear, the reduction rates increases rapidly. When the degree of reduction is plotted against time, it results in a sigmoidal shape. The second model for the reduction mechanism is the contracting sphere model. Reduction begins rapidly, thus forming a metal surface over the oxide grain. Then the overall reduction of the bulk slows down due to the decreased interfacial area. Here, if the degree of reduction is plotted against time, we see a rapid start that slows down as reduction proceeds. When metal oxides are supported, it may behave differently compared to the bulk oxide. For example, when supported metal oxides are homogeneously distributed across the support surface, reduction becomes difficult. Island formations of oxides, on the other hand, typically proceeds in a similar mechanism as the unsupported metal oxide. The technique is quite simple and easy to run in modern instrumentation. A linear heating ramp is applied while a sample is under a constant flow of reducing gas. As the temperature is high enough, reduction begins and the reducing gas is consumed. The plot shown is an example of a TPR on copper oxide supported on alumina. Here we can immediately extract and obtain useful information from the temperature program reduction. 1. The fingerprint of the material. This is important for quality control and material screening. 2. The peak temperature, shapes, and number of peaks. Notice there is a dominant peak followed by an overlapping shoulder at higher temperatures. And lastly, amount of reduction. With calibrations applied, peak integrations can quickly quantify the amount of reducing gas consumed during this TPR. There are a few instrumental considerations to be taken when performing temperature program reduction. This is important not only for good results, but also for ease of use. Accurate and precise control of gas flow is absolutely necessary. Mass flow controllers that are calibrated and operate in a linear range are important for reproducibility of the results, especially for case studies presented here. The sample temperature needs to be measured accurately and with a fast response. In the AutoChem systems, a thermocouple is used for this purpose. The thermocouple is located near the sample bed to accurately measure the sample temperature. Additionally, the time it takes between temperature measurement and a change in signal is dependent on the gas flow rate and temperature ramp rates. Low dead volumes reduces errors if flow rates or temperatures are changed significantly. During reduction, water vapors are formed as the metal oxide is reduced. The system needs to be kept at elevated temperatures and the lines heated in order to prevent condensation. Now, as reduction occurs, the reducing gas concentrations decreases. TPR is typically performed with a binary mixture of the active gas, or the reducing gas, and an inert gas when using a thermal conductivity detector. Signals are detected due to the changes in the conductivity of this binary gas. The TCD is highly sensitive, but requires careful understanding of the gaseous product involved in the temperature program studied. Coupled with a mass spectrometer, it allows information on the composition of the gas. And lastly, calibration of the TCD in systems such as the AutoChem is entirely automated. There is a dedicated reference stream and a carrier stream, as well as a blend valve that automatically collects and blends the gas attached during calibration. Other methods are time-consuming and more prone to operational errors. The selection of the binary gas mixture is important to detect the most sensitive changes in signal. For this reason, a high difference in thermal conductivity of the binary gas is chosen for the most sensitivity. Hydrogen has a thermal conductivity relative to air of 7.07. The best choice for the inert gas would be argon, which has a drastically lower conductivity relative to air of 0.68. Similarly, due to the conductivity of water, which is close to the value of argon, if not trapped, will cause interference with the gas conductivity measurements. There are two methods to trap the water formed during the reduction. Cold traps are low-temperature zones used to purposely trap water prior to reaching TCD. Typically, a dewar with a slurry of liquid nitrogen and isopropyl alcohol is used to create this cold zone. The gas travels to a coil immersed in this cold bath, about -89 Celsius. After it exits the sample tube, the cold trap life, however, is limited. Experiments that require a longer reduction time due to a low heating rate or high temperature ranges may encounter issues. Preparation of slurry requires experience and is time-consuming. Most importantly, it requires more user intervention. Users need to return to the instrument at the start and load the cold trap. A sorption trap is a highly sorbent material and is used to selectively absorb water. This allows a fully automated temperature program reduction study with no user intervention. Sorption life is dependent on the material, but with a zeolite material, it extends well beyond typical TPR analysis time, and even after many experimentations. It could also be regenerated in situ using a heating mantle under an inert gas. Limitations of this are dependent on the type of gases that evolve from the sample. This study is conducted using the sorption trap due to the ease of use. The temperature program reduction profile is affected by the experimental conditions. Monti and Baiker explored the parametric sensitivity of heating rate, hydrogen concentration, flow rates, the amount of reducible species, and how it affected the TPR profile using a pure nickel oxide metal powder. A characteristic number K was determined to aid in the most optimal reduction profiles. The following sections will focus on these parameters to demonstrate the sensitivity of TPR for the 13% copper oxide nanoparticles on alumina support. The K values for this material would then be determined. Some preliminary characterization was done to better understand this material. The sample is a copper oxide on alumina support purchased from Sigma Ultra. Samples are 14 to 30 mesh. Spheres are size 0.6 to 1.4 millimeters in diameter. A Phenom Pro SEM was used to take these photos. The top left is shown 1 millimeter beads with a 70x magnification. The largest picture on the right is 10,500x magnification. Here we can see the nanoparticle dispersed on the alumina support. The nanoparticles are well dispersed with some clusters of a few microns. Additionally, nitrogen physisorption using the TriStar 2 Plus shows that this is a mesoporous material with pores between 2 nanometers to 50 nanometers and a specific surface area of 165 meters squares per gram. Pore size distributions shown here are using BJH. For the temperature program reduction study of copper oxide nanoparticles on alumina support, the AutoChem 3 was used. Several key factors here. I'd mentioned earlier, a dedicated reference mass flow controller for the reference size of the TCD, along with a blend valve that can dilute the carrier stream concentrations to automatically do TCD calibrations. A pre-blended tank was used for the reduction. 10% hydrogen is a typical concentration. For concentration studies, this was diluted with the internal blend valve available in the system. A cold trap was not used. Instead, a sorption trap filled with zeolite was used to sorb the water evolved during the reaction. Additional information was collected simultaneously with a mass spectrometer. This gives further information regarding the gas composition during the experiment. The total gas flow rate is varied while the other conditions are kept constant at 10% hydrogen concentration, a ramp rate of 10 C per minute, and the reducible amount of approximately 160 micromole of copper oxide. From left to right, the blue line is flowing at 100 cc per minute, the middle or red line is 50 cc per minute, and the purple line furthest to the right is flowing at 25 cc per minute. Notice that as the flow rate decreases, the time it took to reach the peak max is increased, and correspondingly, the peak temperatures increase. The peak shape has also changed. The shoulder observed in lower flow rates is much more than the analysis at 100 cc per minute. The graph shown on the right overlays the nickel oxide data from Monti and Baiker. The primary y-axis in blue is the copper oxide, and the secondary axis in orange is the pure nickel oxide powder. When comparing the peak temperature sensitivity of pure nickel oxide to the copper oxide support on alumina, the copper oxide is less sensitive at lower total flow rate than the pure nickel powder. The copper oxide performs closely to the expected models in which he discussed. Other analysis conditions for Monti and Baiker were similar and only slightly different. They used 5% hydrogen, 12 C per minute of a heating rate, and 405 micromoles of nickel oxide. There are two effects responsible: increase in the time lag between temperature measurements and signal detection at lower flow rates. We don't believe this is a significant contribution, as the dead volume in the AutoChem 3 is minimal and may account only for a few degrees. The second effect is the increase in dispersion effects. Copper oxide nanoparticles is much more dispersed due to the supported alumina, as we have seen with the imaging. Here we see the effects of the copper oxide nanoparticles and the support. It allows the copper oxide to be well dispersed, thus reducing the sensitivity changes observed for peak temperature changes when total flow rates are changed. From left to right, the tallest peak is 10% hydrogen, followed by 5% hydrogen and 2% hydrogen. Similar to the effects of the total flow rate, there is an increase in peak temperatures as the concentration of hydrogen is reduced, and there is an increase in brick broadening. Here, other analysis conditions are also controlled and kept constant. A total flow rate of 50 cc per minute, 10 c per minute ramp rate, and approximately 160 micromole of copper oxide. Monti and Baiker performed this with 75 cc per minute, heating rate of 12 c per minute, and 405 micromoles of nickel oxide. Here, when comparing to the pure nickel oxide, while both peak temperatures have similar sensitivities, the copper oxide peak temperature has a bit more sensitivity to the hydrogen concentrations. This may be due to kinetic differences in the reduction mechanism. As discussed previously, there were two models for the reduction mechanism. Copper oxide follows the nucleation model. In the plot on the right, the TPR profile of 10% is shown, and the degree of reduction for 10%, 5%, and 2% is plotted on the secondary axis. When the degree of reduction is plotted against time, the plot is sigmoidal for copper oxide for all concentrations. In the nucleation model, higher hydrogen concentrations affect the growth and nucleation process. This is apparent, as with higher concentrations, we see reduction occurring sooner and increasing at a faster rate. When considering temperature ramp rates, as the heating rate increases, the peak temperature increases. The trend and sensitivity of copper oxide on alumina is comparable to the nickel oxide. Here we use 50 cc per minute, 10% hydrogen, and 160 micromoles of copper oxide, while Monti and Baiker use 75 cc per minute, 5% hydrogen, and 405 micromole of nickel oxide. When considering the amount of reducible species used, as the amount increases, the peak temperature increases. The trend and sensitivity of copper oxide is comparable to the results of nickel oxide. Here we use 50 cc per minute, ramp rate of 10 c per minute, and 10% hydrogen in argon. Monti and Baiker use 75 cc per minute, a temperature ramp of 12 c per minute, and 5% hydrogen. The sensitivity of TPR can be optimized based on the selection of these experimental conditions, with a calculation of a characteristic number K. K is calculated by the amount of reducible species over the total flow rate multiplied by the concentration of the reducing gas. Dimensions are in seconds. When considering all the parametric sensitivities, the following criteria were proposed by Monti and Baiker. At least 10% of the reducing hydrogen gas is consumed, and at most 66% of reducing gas is consumed. These considerations will allow the determination of the range of reducible species under specific analysis conditions to get the K values. A characteristic K value determined for nickel oxide was 55 seconds at a heating rate of 0.1 Kelvin per second and 140 seconds at a heating rate of 0.3 Kelvin per second. To demonstrate, a plot of the maximum active gas consumed and amount of reducible species for copper oxide on alumina is shown. The initial active gas flow is 3.718 micromole per second, or 5 cc per minute. The low heating rate determines the first criteria, as it sets the lowest value for the amount of reducible species based on the minimum consumption criteria. Here, approximately 115 micromole of copper oxide would set the lower value. Similarly, the highest heating rate expected to be used would be the limiting factor for the maximum gas consumed. Here, at a heating rate of 20 C per minute, this would be approximately 350 micromole. Here is an example calculation from the data gathered on copper oxide. With the minimum and maximum reducible amounts determined from the previous graph and the analysis conditions used for this collection, a K value of 37 seconds through 113 seconds was determined using a similar heating range as Monti and Baiker. This K range is shifted to lower values as compared to the nickel oxide data he presented. In the second case study, we looked at copper oxides and compared it to the bulk copper oxide. The copper oxide nanoparticles on alumina is compared to the TPR of a pure copper oxide powder less than 10 microns. Here the peak temperatures are relatively the same. However, the shape of the TPR is drastically different. The pure copper oxide is more broad, with the reduction occurring over a longer period of time. The shoulder of the pure copper oxide is more apparent. If we look at the degree of reduction, the pure oxide begins reduction much earlier than the supported copper oxide. However, once reduction begins, the rate of reduction of the copper oxide on alumina is much quicker, possibly due to dispersed nanoparticles. Here, the effects of the support material is observed. The interactions with the support increases the temperature at which reduction begins. Previously, it was shown that the sensitivity of the total flow rate for the supported copper oxide was less compared to pure nickel oxide, especially at lower total flow rates. This was revisited. The pure copper oxide results is overlaid in the previous graph and sharing the same primary y-axis as the copper oxide supported on alumina. Here it is apparent that the pure copper oxide peak temperatures exhibits more sensitivity to the total flow rates similar to the pure nickel oxide. The dispersion of the copper oxide nanoparticles on the alumina support reduces sensitivities to the total flow rates, especially at the lower flow rates. This brings us to conclude the current case studies on temperature program reduction. Here we discuss the importance of not only experimental conditions, but instrumental as well for best results and ease of use. We show how analysis conditions such as heating rates, total flow rates, gas concentrations, and amount of reducible species affects TPR and its sensitivity to these changes. We show how these conditions can be used to calculate the characteristic K values for the example of copper oxide and alumina. And finally, a comparison to bulk copper oxide powders was presented to further illustrate how the supported copper oxide affects the temperature program reduction profile and its sensitivities to total flow rate. Although it appears that temperature program reduction is a simple method, it is seen here that many parameters discussed has an effect and should be considered when performing a TPR. Thank you for your time and for attending this webinar.
Thank you, Hong. I'm opening the chat for everyone's questions now, and we already have a few. You showed really nicely this comparison between your copper oxide and the nickel oxide from the historical studies. How long does it take you to conduct one of these studies?
That's a very good question, Jeff. The TPR study itself is really dependent on the temperature rate. So when we increase the temperature at 20 versus 1.5 C, and the range and the total range of temperatures that it can factor into how long it's going to take. Here we only go to about 400 C, and at 10 C per minute, that's about slightly less ambient. The really good thing about the AutoChem 3 that I didn't really mention is that we do have a cooling device that allows the system to cool down after the experiment, and that does have a factor on how long analysis takes as well. With the vortex cooler on the AutoChem, it can cool down from 400 to ambient, less than half an hour. I don't have the exact time, but comparably speaking to other methods, it's really fast. So the total time for this, start to end, let's say at 10 C per minute, that's about 2.5 hours.
Okay. Thank you. And also, you showed this very nice comparison between supported copper oxide and pure copper oxide. The supported copper oxide had a very narrow peak versus the much broader pure copper oxide peak. Is there any influence of particle size on the pure copper oxide versus perhaps a much controlled finer particle size for the supported copper oxide?
The pure supported oxide or nanoparticles, and they're very well dispersed. When I looked at the pure copper oxide, they're powders and they're compact. They're a little bit harder to control in terms of sampling for the pure copper oxide powder because smaller particles sometimes may raise, and it depends on how you sample. It's hard to control the particle sizes of pure copper oxide. When we look at the TPR profile, the supported copper oxide, the dispersion of it and the size of it, I believe that allows the hydrogen gas to be able to reach it fairly easier than the pure copper oxide, just because of how well dispersed the support material is able to allow it.
Can you discuss a little bit about potentially using metal, looking at this for understanding metal support interactions?
Yes. So some of the results shown, the support material itself increases the temperature at which reduction began, and I believe that's a interaction due to the support. So it's allowing the reduction, or it increases the activation energy in which reduction is needed. So if you compare the pure copper oxide versus the supported one, not only the initial, the reduction temperature increase, and that's mainly due to the support interaction.
Have you seen any other interesting papers on this particular topic besides Monti and Baiker?
Yes.
I know there have been some complementary publications.
Yeah, there's Malay and Caballero as well. They explore the analysis conditions on TPR, and it's also a very good read. There's also more modern publications on copper oxide using in situ techniques such as X-ray diffraction. So if you want to verify the actual oxidation states of copper itself as it goes, that's available as well. I believe in some of those studies they do isothermal testing. So there are modern techniques as well that can give information for you.
That's all the questions we have time for today. If we haven't been able to get to your questions, one of our application team will be in touch shortly. Hung, is there anything else you'd like to mention?
This was a very interesting study. Fortunately, the instrumentation really made it easy. With the Schwarzman trap, I didn't have to babysit the instrument. And with the cooling device, it really helped me, it really shortened the time for me to actually go back and start the new experiment. I didn't present the mass spec data. Mostly it was used for me to make sure that the gas composition during the analysis is not really affected by anything coming off. I did see small bits of carbon dioxide, and other gases, but that's something else that I don't believe have a huge influence on the actual sensitivity for peak temperatures. It may have an effect on the quantification part. But other than that, thank you everyone for attending, and I really appreciate it.
Great. Thank you everyone for attending today's webinar. If you have any feedback for us, we'd be grateful if you could complete the survey, which will be distributed in our follow-up email. We hope you found the session beneficial. Do not forget to check back for upcoming webinars on micromeritics.com/webinars. We hope to welcome you again soon. Thank you.